wanted to just yap about some numbers and math topics for you guys because I thought it would be fun. I have a few I want to bring up, but I won't go to too many since there's a lot of fun topics that exist. But the first one I wanted to talk about is Euler's number. And it's a constant that we can calculate by referring to compound interest. So if we take a step back and we look at an equation that you might have seen before, but it's a equation that, if I go ahead and write it down, has a few values here. Now, if we take a look at this, we have A as the amount after compounding. We have P, which is the principal value. That's going to be the first number that you start with. We have R, which would be the rate. And this will be like your 5%, 10%, 15%, all that. And then we have N as the number of times we want to compound. So let's say we compound quarterly. So we'll say 4 times in a year. If we want to do monthly, that's 12 times in a year, etc. And then we have T. And T is the time. And that's usually measured with years. So if we want to do compound interest over, let's say 3 years, we'll put a 3. But that's not what we're going to be doing here. What we're going to be doing is manipulating it a little bit so we can go ahead and mess with it to see how we can get Euler's number. So let's say we start with $1, since that's a good place to start. We're going to go ahead and say we're going to be using a rate of 100%, so that would just be a 1. And the number of times, I'm just going to leave as n. And then we'll go ahead and say it's going to be n again. And for t, what I'll just say is this is going to take place in 1 year, just to help make the math simpler. So we have this new expression here we can write as 1 plus 1 over n to the power of n. If you were to get n, and let's start with 1. If we go ahead and calculate that, we'll get 1 plus 1 over 1 to the power of 1. Now, if we go ahead and do that, that's 1 plus 1. That's 2 to the power of 1, so that'll be 2. So the value is 2. Now, I won't go into more details because that's a lot of math that, I'll be honest, I don't want to do by hand. But this beginning number is quite important because if we get n, and since this means the number of times we want to compound, let's just make it really big. So let's change it to, let's say 10, or maybe 100, 1,000. Well, if we keep on going higher and higher, eventually it approaches infinity. And since infinity is not a number, we can follow infinity as a concept. So as this n gets really, really, really big, as it approaches infinity, this answer we actually calculate starts to form 2.71828, and it goes on and on and on. Now, this number is Euler's number. This is represented by the letter E, and according to Euler, it's the letter he had left, and it's not named after himself. But this is the same number that when you write an exponent of e to the x, or when we're talking about exponential growth, That's what that is, because it comes from exponential growth. And so it's just a fun little thing that you can calculate. The next number or idea I want to talk about is Avogadro's number. And simply, this number is an estimated of 6.022 times 10 to the power of 23. Now, this number is very large, yes, but this number represents the number of particles, such as like atoms, molecules, in 1 mole. And 1 mole is a measurement in chemistry. We talk about how much something is, and it's used as a branch between like talking about atoms to something more like something we're used to, like grams or density, honestly. So, where is it used? Well, let's make the math easy. Let's say we have 1 liter of water, right? Now, 1 liter of water is 1,000 milliliters, and because water is used as a baseline, this has a density of 1 gram per milliliter. And what we can do with that is go ahead and, if we were to multiply these out, these units cancel. So we end up with 1,000 grams. 1,000 grams is what we're going to be using. So this is a kilogram of water, essentially. A liter of water is a kilogram. Now, the molar mass, which I won't get into here, molar mass of water is about 18.015 grams per mole. Now, this is a approximated value that's been calculated, but we'll go ahead and use it like this. If we then use a similar thing here, we have 1,000 grams, and now we want to cancel grams, so we're going to be flipping it over. So we're going to have something like this, 18.015 grams per mole. These units cancel, and we can calculate that it's about 55.5 moles. Now, what does that mean? If we get 55.5 times this big number right here, so 55.5 mole times this 6.022 times 10 to the power of 23, we can actually calculate how many molecules of water there are, which means those little molecules of H2O, we can exactly calculate how many there are. If we multiply that out, that's about 33.4 times 10 to the power of 25, which is, it's 33 with 24 zeros. I put the decimal place here wrong. But there's 24 zeros in this number. And that's just an approximation. There's a lot more, but we're making it even easier for us to calculate. But there's a lot of zeros. And that's how we can calculate. We can further go on and figure out, well, how many are hydrogen atoms? How much are oxygen? But we can actually calculate how many atoms there are in 1 liter of water. And we can do that with other molecules as well. This next idea is the Fibonacci sequence. This one has a bit of charm with nature, so you'll see it in nature, and it's pretty fun, and it's considered very pretty. But its origin is here with starting at 1, 1. Now, how do we calculate the Fibonacci sequence? Well, we simply just add the previous two values. 1 plus 1, 2. 1 plus 2, 3. 2 plus 3, 5. I know, adding is very hard. And then we get 8, 13, and 21. And I'll stop here because it gets, it's very long, but we get the sequence here. Now, there's a few things that we can talk about this, but one of the things I do like is if you were to take the number here and you divide it by the previous number, you approximate the golden ratio, which is another idea that comes from the Fibonacci sequence that talks about kind of perfect, I don't want to say perfect, but like a ratio that humans tend to kind of favor over another. It's seen with like in nature, like if you look at a picture of a sunflower seed, like the sunflower, like the seeds are placed in a certain way, or flower petals. There's a lot of like psychological things that we can see. But one of the other things here is, what if we get each number and we turn it into a square and we place them next to each other? So the first number is 1. So go ahead and draw a square with 1. Now the next number is 1. But we're going to go this way. Now the next one's 2. And now we can actually see that there's a length of 2 right here. So I'll draw 2. And now the next one is 3. But we see that there's a length of 3 here. So we'll use that to help us draw a square. And the next one is 5. So go ahead and go 1, 2, 3, 4, 5. And go all the way up to 5. Now, I can continue on, but it gets really big. But you can actually see the pattern that it forms here. So if we start here, and we kind of draw a circle using this corner as the center, and go like this. Now this is a very poor drawing of it, but you kind of get the idea. Let me draw that again. You get this spiral that forms out of these squares. And this is known as the Fibonacci spiral, or a spiral. And we can kind of see this when you look at shells or anything like that, but it makes it a really nice thing. And in some cases, not everything, if you place this rectangle shape on there, you can kind of see how your eyes kind of see it's like, if you look at a certain thing, it may be chopped in half, visually appealing. There's like some aspect of it that makes it look nice. But that's the Fibonacci spiral. Now, another one that's less, I would say, visually exciting is some trigonometry. Personally, I don't like trig, but I use it so much, I don't think I'm allowed to say that. But we can start with, you might be familiar with SOHCAHTOA. SOHCAHTOA. And this relates that if you have a, oh, this is in the way. Let me move this real quick. If you have a right triangle, like this, we can actually get some values from there. So if we wanted to calculate this angle, what do we need? Well, let me call this length A, B, and C. SOHCAHTOA is sine. The ka is cosine. And TOA is tangent. sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent's opposite over adjacent. So what does that look like on the triangle? We're looking for this angle here, so we need the opposite, and that's going to be this one divided by this one. Now, from this, you can use it for, I would say, different things, but the way I use it the most is when you have let's just say, a surface, and you have, like, let's say, a vector pointing this direction at an angle of 30 degrees. When we're doing some analysis here, we want to figure out how much it goes up, how much it goes right to the right. Now, this is not to scale, so we can't just measure it. And what we can do is, well, how much is it going to the right? Well, if we call this length right here, we'll say F for like a force or something. And we want to see how much it goes to the right. Well, it's going to be F cosine the angle. And what does that look like? Well, if this F is the hypotenuse and cosine's the angle, and we're looking for how much it goes to the right, so the side that's touching the angle, if we go back to cosine, it's adjacent over the hypotenuse. And so cosine is the adjacent over hypotenuse. This is the angle. So we have an angle of 30. We want to find out what is this adjacent number. So we multiply h on the other side. So cosine angle, what's that, 0? Cosine of angle equals adjacent over hypotenuse. So we want to multiply the hypotenuse and move it to the other side. And that's what we did here. F cosine 30. And for the up and down, what we'll talk about is F sine of 30. And that's what we'll go ahead and calculate to get the up and down value. Same thing with cosine. This is going to be the sine. We want to find what's this opposite value. And what we have to do is, we know the angle and we know the hypotenuse. So sine of the angle is going to be opposite over hypotenuse. So what do? We multiply the hypotenuse, so those cancel, and hypotenuse times sine of 30 degrees. And then we go ahead and get the opposite value. And that's it for that. Another thing about trig that when I discovered it, it kind of like helped me out with understanding of where it comes from, is this right I showed you, but also tangent. Tangent always confused me. I didn't understand it quite at first, but the thing that really kind of sealed the deal was, well, tangent has another form, right? It's not just always opposite over adjacent. It's also, let me find some space I can write this. Let's see, where can I write this? Let's put this over here. Tangent is, for me, what I can say is basically the, I'm going to say quote unquote, the slope. What does that mean? Well, in a unit circle, I'll move this so it's a bit centered better. When you have a point here this is represented by cosine, comma, sine for whatever value. And how do we get tangent? Well, it's going to be sine over cosine. And the thing that really helps me understand it is understanding it as x, comma, y. Y over x. And what is this? Rise over run. And when I relearned that, it was basically a slope. I was like, that really clicked, and I was able to understand that. So when we have this, now cosine represents the up and down. So if this line right here was, let's say, circling, at every point we'll see cosine taking however far left and right it's going, and sine's talking about how up and down. And that's why when you look at a graph of sine and cosine, they're almost the same, but they're off by exactly 90 degrees. Now this drawing doesn't show that, but it was just to give a visual. The other thing I wanted to talk about was the floor and ceiling functions. This is it's rounding, essentially. It's a different form of what rounding we normally see. Now, when we say rounding, we normally look at a number and go, oh, we can round that down to 20, or we can round 25 to 30, right? But let's say we always need to round up. We always need to round down. What does that mean? Well, let's say you're playing a video game and you're on level 10. And now there can maybe an experience bar that's continuing, but whenever you look at your level, you always say level 10. You never say level 10.75 or anything like that. You always say level 10. And until you reach the next level, you always say the level that's directly below you. So that's why you say level 10. Now, this is called, and rounding down is the floor rounding. And we normally see these in programming in that cases, and sometimes some more kind of like more math, more like mathy math, like more pure maths, but we don't really see this too practically. The ceiling function is the opposite. It's when you round up. So no matter what the number is. So this right here, even though it's 10.75, you're rounding down, even though it would round up to 11. The ceiling function goes to the upper number. So in this case, let's say you're counting the number of cars that need to take a certain number of people. So let's say 10 people can fit into a car, and there's 24 people. Well, we have a car here. We'll have an extra car. Well, how many cars do you need? Well, there's 24 people, so you can finish. We'll fill up this 2 cars with 10 people, which leaves 4 people left over. Now, we're taking everybody. We're not leaving 4 people behind. We would need an extra car to fill up with 4 people. So how many cars? 1, 2, 3. So this is where you would round up. Personally, I've done this where, let's say we're calculating forces onto something, and let's say the force that I get is like 12.35. In some cases, it's better for me to just go, oh, that's 12.5 or maybe 13. It's why some cases, some people say gravity's acceleration due to gravity, the 9.81 is rounded to 10. It's an approximation because in my case, like here, is if I'm calculating something that needs to hold 12.35 pounds or newtons or whatever, it's better to overcompensate a little bit, and then there's other steps in the future that will help like keep the cost down. But this is an example where I would round up like 12.35 round to 13 because it helps makes the math easy. I don't have to do with decimals. 13's not a nice number to round with, but it's to multiply with, but it's a bit better than having ugly decimals in there because it's faster to calculate. The last one here I want to talk about is the Strobogrammatic Numbers. Now, I learned this last week or so, and I've seen it before, but I didn't know it had a name. These are numbers that look the same upside down. What does that mean? Well, if I write the number 1, if I completely flip it upside down like this, it looks the exact same. If I write 10, well, it doesn't look the same anymore because now it looks like 1. But what if I change that number to 101? Well, flipping it, it's still 101. And there's some other numbers that look the same, such as 8, 6, and 9. Now, 1s and 0s look the same when you flip them. 8, 6, and 9 depend on where you place them. So 8 upside down looks like an 8. A 6 upside down looks like a 9. And a 9 upside down looks like a 6. And so you have to be careful how you place it. But if you say 96 and you flip that upside down, now the way I wrote it, it looks kind of bad, I'll be honest. But it's 96 upside down. So if I were to write 808, or like I said, 101, writing these upside down will be if I flip them, and go ahead and just like rotate it, it will be the same number. Now this, writing it like this kind of makes it ugly, but if I were to write it using a 7-segment display, which you've seen before on like numbers, they're the ones that kind of look like this. It has a nice like uniform look to it, and that's why when you flip it, it can look the same. So like an 8 looks really pretty both ways. That's why my 96 looked weird, because it's the way I wrote it. But a 7-segment display, which you've seen before, like in clocks, I know some just various like I know different fonts will make it look like that. It's not used too commonly actually anymore, but I think they're really nice because they're very simple and like straight to the point. But if you were to write a 9, well, you would just write it like this, and then you were to write a 6, and it looks like this. Now if you were to flip this around, it looks like a 96, and it looks a lot better than when I was writing it. Now, that's a lot of numbers, and it's only a few topics too, so I don't want to go too crazy, so I'll go ahead and wrap up here at like 30 minutes. But if you want to see more math yapping, you can comment of what math ideas you want me to yap about. I tried to do this take before, but my laptop messed up, and then I have airplanes in the background, but I'm not going to even bother with that because I don't think they're that distracting. I'll just fix up the video. But I hope you enjoyed. I apologize for the long wait. I've been dealing with a lot of stuff here, but until I see you next time.